Hey, this is Mr. Ayton. This is Pre-AP Chemistry, and it's Unit 6 Chemical Reactions. We just finished up Unit 5 Chemical Reactions in Week 10. We took a look at our precipitation reactions. We took a look at oxidation reduction reactions. We looked at what chemical reactions were, but now we are in Week 11. And Week 11, we're finishing out chemical reactions. We're going to take a look at acid and base reactions, combination and decomposition, and lastly, combustion reactions. So let's first take a look at what's called acid-base reactions. Acid-base reactions are all about strong acids and strong bases, or weak acids and weak bases. We know an acid has a pH below 7, and bases have pHs above 7. And when we have a strong acid like HCl, you can see HCl is going to dissociate 100%. It's going to ionize when it's in water 100%. It's going to split up in H plus and Cl minus. So if you have a strong acid, you can literally just write H plus. If we look at a list of some strong acids, we have hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, H2SO4, and HClO4, which is called perchloric acid. But you don't have to write HCl. You don't have to write HNO3. You don't have to write H2SO4. All you have to write is H plus, because these dissociate 100%. You don't have to worry about their spectator anions here. All you care about is H plus. Well, strong bases do the same thing. Strong bases will dissociate 100% when it's in water as well. Sodium hydroxide will split up in Na plus and OH minus, which means strong bases, all you care about is OH minus. Some examples of strong bases are like lithium hydroxide, sodium hydroxide, potassium hydroxide. You can see alkali metal ions with hydroxides. And guess what? You don't have to write NaOH. You don't have to write LaOH. All you have to write is OH minus because it dissociates 100%. But weak acids and weak bases don't dissociate 100%. They don't split up, which means you're going to have to keep the weak acids together or the weak bases together, and weak acids will donate H+. They're going to give away H+, because they're H+ rich. And weak bases will accept H+. Okay, and we'll take a look at some examples of those. Let's take a look at our first example of an acid-base reaction. We have hydrochloric acid, which is a strong acid. What do we put for hydrochloric acid? Do we have to put HCl? No. We just have to put H+, because it is an aqueous solution. It's a strong acid. We don't care about the spectator ion. And it's combined with a strong base, sodium hydroxide. Do we have to put NaOH? No. We're going to put OH minus because it dissociates 100%. And what happens when you put H plus and OH minus together? You get HOH, or we call it H2O liquid. It's a neutralization reaction. And let's take a look at if we're balanced here. We have two H's in the reactants, two H's in the products, one O in the reactants, one O in the product. You have positive one, negative one, which is a zero charge. A liquid is a zero charge here. So we're balanced with atoms as well as with charges as well. Okay, let's take a look at when we combine a weak acid with a strong base. Here we have acetic acid, otherwise known as vinegar, C2H3O2, and it's aqueous. Can we split up this weak acid? No, because it's weak. It does not dissociate 100%. And it's going to combine with a strong base, sodium hydroxide. Do I have to write NaOH? No. I'm going to write OH minus, which is aqueous, because the strong base dissociated 100%. So here I have a weak acid with a strong base. And what did we say weak acids do? Weak acids will give away H+, won't it? And so what happens when this substance gives away H plus to OH minus? Well, H plus and OH minus makes water, doesn't it? Liquid water. And what happens to this C2H3O2 when it loses an H and loses a plus? Well, if it loses an H, it becomes C2H3O2. If it loses a plus, it becomes a minus as well, okay? And you can see on this side, this substance that does not have any more of that H+, we call that a conjugate base, whereas this substance that gained the H+ is a conjugate acid, And take a look, everything's balanced, isn't it? You can see even the charges, we have zero charge and -1. That's a -1 overall charge on the left side. You have a -1 overall charge on the right side. You can see this is called an acid-base reaction. Okay, well, let's go to what's called combination reactions. Combination reactions. And combination reactions is exactly what it sounds like. You're combining two things together to make one product. Combining two reactants together to make one product. So here we have metals and oxygen gas will make metal oxides. Let's take a look at an example. Let's take a look at a metal like magnesium. I'm just picking any metal here. Magnesium solid and oxygen gas, and that's going to make magnesium oxide. Now, what happens when magnesium and oxygen come together? That's an ionic compound. Magnesium's positive 2, because it's an alkaline earth metals. Oxygen's negative 2, which means you need a 1-to-1 ratio. That's an ionic solid here, isn't it? And you might say, Ayton, why isn't it MgO2? Well, we're going to do a thing called balancing the reaction. Balancing the reaction. And what balancing the reaction means is magnesium, you have a conservation of mass. So we have one magnesium. We're balanced. We have two O's, but we only have one O at the end. I can't change this formula, MgO, because that's the formula of magnesium oxide. So I'm going to put a big 2 as what we call coefficient. And this 2 goes to the magnesium as well as to the oxygen. So you can see now we have two O's and two O's, but this whacked out my magnesiums. I now have two magnesiums. So I'm going to put a big 2 right there as well. And I have a 2 to 1 to 2 ratio, and that balances my atoms as well as my charges. And so we're going to use coefficients to balance the reaction. Okay, once we get our formulas, then we can balance our reaction. The next combination reaction we're going to do is called a non-metal and oxygen gas. Let's pick a non-metal and oxygen gas. Let's pick hydrogen gas and oxygen gas. Well, what happens when we put hydrogen gas and oxygen gas? We're going to make a non-metal oxide. So what's the non-metal oxide when hydrogen is with oxygen? That's H2O, H2O gas. And you might say, Mr. Ayton, why don't we put H2O2? Well, because that's not what actually happens. It makes H2O. That is my non-metal oxide. But I can balance my reaction. I have two H's at the beginning, two H's at the end, two O's at the beginning, only one O at the end. So I'm going to need a coefficient of 2. But again, that whacked out my hydrogens, so I'm going to need a 2 right there to balance my hydrogens. And again, I have a 2 to 1 to 2 ratio. Okay? Let's take a look at a third reaction. Let's take a look at a non-metal and hydrogen gas. Let me pick a non-metal. Let me pick nitrogen gas, and I'm going to pick hydrogen gas for hydrogen gas. And this is going to make a non-metal hydride. What happens when nitrogen and hydrogen come together? It's going to make ammonia, NH3 gas. And again, I'm going to balance my reaction. I have two nitrogens at the beginning. I only have one at the end. So I'm going to put a big 2 there. So that balances my nitrogens. But my hydrogens are off. Do you see how we have 2 times 3 is 6 hydrogens? So I'm going to need a 3 here to make 6 hydrogens. And that gives me a 1 to 3 to 2 ratio for this combination reaction. Okay? We have 2 more combination reactions. One is called a metal oxide and water. A metal oxide and water. Let's take a look at this metal oxide up here, this magnesium oxide. I'm going to take that magnesium oxide. Oop, I'm going to fix that a little bit. MgO, and that's a solid. And that's going to combine with water. And that's going to make a base, magnesium hydroxide. Magnesium hydroxide. And magnesium's got a positive 2. Remember, hydroxide's got a negative 1. So that gives me MgOH2. And I might have to balance this. Let's see if I do have to balance this. I have 1 magnesium at the beginning, 1 magnesium at the end. I have 2 O's, and this 2 goes to 2 O's. 2 H's, which means this is already balanced, a 1 to 1 to 1 ratio there. Last but not least, let's take a look at a non-metal oxide and water. Let's take a look at a non-metal oxide like carbon dioxide gas. What happens when carbon dioxide gas gets put with water? These are going to combine together to make an acid, H2CO3, and this is going to make what's called carbonic acid. And so when you have non-metal oxides in big cities mixing with the water in the air, it makes acid rain, it makes acid in the clouds, and this ends up happening. This is all balanced as well. So nice combination reactions here. 5 of them that you might want to practice. We also have what's called decomposition reactions. Decomposition is exactly what it sounds like. It's decomposing. It's breaking down. Let's take a look at a metal oxide. Let's take a look at something like let's take a look at calcium oxide solid. You could heat calcium oxide solid, and it's going to make calcium and oxygen gas. Calcium, oxygen gas. We're going to have to balance this reaction. You can see we have 2 O's at the end, which means we need 2 O's at the beginning. We need 2 calciums, and this is a 2 to 1 ratio. Another example is a metal carbonate. Let's take a look at magnesium carbonate. MgCO3 solid, and this is going to break down into a metal oxide, magnesium oxide solid, and carbon dioxide gas. And I believe this is already balanced. Let's see, 1 magnesium, 1 carbon, 3 oxygens, 1 and 2, which is 3 oxygens. And this is metal carbonates will break down into metal oxides and carbon dioxide gas. And probably our most important is a metal peroxide, something like hydrogen peroxide. Yes, that hydrogen peroxide bottle that you have in your cabinet at home. This is going to break down into a metal oxide, which is, in this case, it would be H2O, liquid, and oxygen gas. So why do they put it in those brown bottles? Because that metal peroxide will break down into water and oxygen gas, and you don't want to buy a $2.30 bottle of water and oxygen gas. So they put it in brown bottles so it doesn't break down. I believe we have to balance this because take a look. We have 2 O's at the beginning. We have 2 and 1, which is 3 O's at the end. So this, we're going to put a big 2 right there to make these oxygens even. So that gives me 2 O's, and 2 O's is 4 O's. We'll put a big 2 there, and that balances everything out 2 to 1 ratio. 2 to 1 ratio. Last but not least, we have combustion reactions. Combustion reactions is when we're taking a hydrocarbon and burning it to produce carbon dioxide gas and water. Okay, let me give you the most famous formula. That's propane, C3H8 gas, and you burn that with oxygen gas. And guess what you make when you do that on your grill out back? You're going to make carbon dioxide and water. And we do have to balance this reaction. Take a look. We have 3 carbons at the beginning, which means we need 3 carbon dioxides at the end. We have 8 hydrogens at the beginning, which means we need 4 times 2, which is 8 hydrogens at the end. Now let's count up the oxygens on my product side. I have 3 times 2 is 6 oxygens. 4 times 1 is 4. So 6 and 4 is 10. So what times 2 equals 10? 5. This is a 1 to 5 to 3 to 4 ratio for a combustion reaction. Well, I hope that that worked out for our chemical reactions, Unit 6, Week 11. That's pre-AP chemistry, and we will be working on that in class. I'll catch you in class. Homies, see you guys. Bye.